Okay, very exciting. We only have two practice problems here in chapter 13. Let's get to it. Practice number one. A researcher wishes to find the best method to lower the blood pressure of patients. Subjects are randomly selected and assigned to one of three groups. The first group takes medication. The second group follows a special exercise program. And the third group follows a special diet. After 4 weeks, the decrease in blood pressure for each patient is recorded as shown in this table. Okay, let's take a look at that table. So we've got the medication, the exercise, the diet. So we can see there were 5 patients. If you look at the medication column, we see how much their blood pressure decreased. One patient went down by 9, the next by 11, the next by 9 again, the next by 14, and the fifth patient, their blood pressure went down by 10. Below that, we see the sample mean of 9, 11, 9, 14, and 10. Turns out that mean is 10.6. That's just provided for us here. And below that, we see S1 squared. Well, if you remember, S squared is the variance from way back in chapter 2. S is the standard deviation, S squared is the variance. So they go ahead and provide us the variance for that first group is 4.3. We see the next column are the people who followed the special exercise program and how much their blood pressure went down: 6, 8, 4, 10, and 8. So those are the 5 patients in that group as well. We see the average 7.2, and we see the variance for that sample as well, 5.2. Finally, we see the folks, the 5 people who followed the special diet. Their blood pressure went down 8, 9, 12, 8, and 15. And we see the average of those 5 values, 10.4. And we see the variance of those 5 values at 9.3. Okay. At alpha equals 0.05, test the claim that there is a difference amongst the means of blood pressure reduction. Okay, so we're going to go through our hypothesis test. We're going to start, of course, with the null and alternative hypotheses, the test statistic, computing the p-value, comparing the p-value with our significance level, and finally deciding to reject or fail to reject based on that comparison. So how are we going to do this? Actually, we should get to the null and alternative hypotheses first. How are we going to do the test statistic? Well, we'll do that in Statcrunch, but getting ahead of myself, how do we set up the null and the alternative hypotheses? Okay, so if you remember, the assumption is always that the means for each category are equal, the population means. So there's a couple ways you could present that. The easiest, one way, not necessarily the easiest, but one way to do it is to say, okay, null hypothesis, all population means are equal. You could be specific to the individual problem. You could say the population means for ways to lower blood pressure are equal. You know, medication, exercise, and diet. I'm okay if you just say, hey, this statement right here, all the population means are equal, and our 3 populations are medication, exercise, diet. Another way you could write the null hypothesis is actually in an equation style. This is kind of a neat way to do it. We have 3 categories, right? So we could say mu1 equals mu2, which equals mu3. The population mean for medication equals population mean for exercise equals population mean for diet. And that's kind of a nice way to avoid the sentence. How about our alternative hypothesis? So the alternative hypothesis, well, we don't really have a neat equation for this. You kind of just have to write that sentence. So what are we saying? If we're going to assume that they're all equal, then the opposite of that would be one of them, at least one of them is different. So our alternative here, at least one population mean is different from the others, from the other two in this case. Now what's nice about the one-way ANOVA test, these are always going to be your null and alternative hypotheses. The only thing that might change, if you like that formula style, that equation style here, be sure to list the number of groups you're dealing with. Here we're dealing with 3 groups, so we have 1 equals 2 equals 3. So other times you might have more than 3 groups, so be careful about that. But hey, as far as your alternative, this is always it. At least one of those means is actually different, is what we're trying to investigate. Okay, very nice. Now the exciting part. How do we compute the test statistic? I'm going to do a separate video showing you guys how to do this in Statcrunch, and you'll see my Statcrunch page. But for now, I just got to kind of walk you through it. Okay. To find the test statistic that we refer to as F here, say, okay, you're going to take the data that you see in that table, and you're going to enter that in as columns into Statcrunch. So enter the data, and when we say the data, we just mean the data for how much the patient's blood pressure went down. Don't include the X bars or the S squareds at the bottom. So why are they, you might ask, well, if we're not going to include those, why were they presented to us? So turns out when you see journals and statistical paperwork and that sort of thing on studies, usually they include those things at the bottom. If they did an ANOVA, you'll see the X bar for each category. You'll see the S squared for each category. But as far as computing the test statistic goes, we don't want that entered into our columns. That's going to mess everything up. So we want it in the problem because that's the way we see it in the statistical literature. But we don't include it when we're actually doing the test statistic. Okay, so just the data from each of the 5 patients, not the X bars, the S squares, put those as columns into Statcrunch. And you may even retitle each one of the columns, medication, exercise, diet. That might make things go a little smoother as well. Okay, once you have all those 15 numbers entered as 3 columns, what are you going to do then? Okay, you're going to go to Stat, and about halfway or so down, you're going to find an option that says ANOVA. You hover over that, and then you select the one way. Click on one way, and it'll give you another box, at which point highlight all of the columns that were used for your data. So it's probably the first 3 columns. You have to click all 3 of them so they're all highlighted. That's all you need to do. Then hit compute. Once you hit compute, it's going to give you a large table. So I'm not going to try and copy that down here on my page. I'll show you it to you when we do the Statcrunch video in a second. Once you hit compute, just kind of look at that. It gives you all this information, and you're going to see MS, and you're going to see SS, but you're going to find F as well. And in this case, if you enter in the data for those 3 categories, and you follow my steps here, somewhere kind of toward the bottom right, you're going to find F equals, and I rounded this to 2 places. I think there were a few more decimal places there in Statcrunch. 2.90. So there's your test statistic F. Statcrunch does the whole thing. We don't follow any formula. We just put in that raw data and click, click, boom, we got it. Now, if you've been following me in your Statcrunch, you probably saw something right next to that F value. They actually provide the p-value as well. So we don't have to do any extra step to get the p-value. They tell us the f, and at the exact same time, they tell us the p-value too. It's pretty nifty. So we can just take that p-value right there. We don't need to go about finding it any other way. Okay, let's kind of think about this for a second. When you look at that data, maybe just look at the x bar 1, x bar 2, x bar 3. Now what we're trying to do, remember what we assumed that all of the population means are the same. And what we see there in that chart are the sample means, 10.6, 7.2, and 10.4. Now, two of those look really close to one another, right? 10.6 and 10.4. 7.2 does not look all that close to the others. However, also think about the variances. How spread out is that data? Well, the 10.6 had the smallest variance at 4.3. The variance of the exercise column was a little bit bigger, 5.2. The variance on the diet was quite a bit bigger, just about double the others, not at 9.3. So we're kind of taking all this into account. We're saying, okay, well, I see what those sample means are, but I also see the variances. And so, again, the formula to do all the calculations, fairly complicated. Obviously, Statcrunch is doing that for us. But it came out with an F of 2.9. Now remember, what's going on with F? If F is close to 1, then that's kind of what we expect. That's our assumption, that F is going to be pretty close to 1. So the further away it gets from 1, the more likely it is that one of these means is actually different from the others. Now the variances obviously play a role in that as well. So we came to a p-value of 0.0936. We say, okay, we'll compare that to our alpha. Of course, our alpha here, 0.05. So the 0.0936 was the bigger one. And if the p-value is larger, what does that mean? In this case, we fail to reject the null hypothesis. We could probably say, it looked kind of to the eye when we were looking at this data like the exercise was not as helpful for lowering blood pressure as the medication or the diet. But, we go through the whole test, we see, okay, we're kind of suspicious of that, but do we have enough evidence? And it turns out no. We got a 0.0936, not especially close to 0.05, so we failed to reject. And if you wanted the interpretation of that fail to reject here in the context of the problem, we might say there is not enough evidence that at least one blood pressure treatment has a different mean decrease than the rest of the treatments. So we're kind of suspicious. Maybe, if we really thought that exercise was not as helpful as the other two, we could probably collect more data and do this test again. Okay. Very good. Let's stop here. We'll do practice problem number 2 next.